Rachel Lee, and I'm a grade 11 student at Chadwick International and also a member of the KGSEA Math Circle. And today I'll be talking about miscellaneous number theory. The first number theory that I'll be talking about that comes up a lot in different AMC questions as well as AME questions is numeric palindromes. And there are something called word palindromes that are the same when they're flipped horizontally. So for example, things like 우영우 or wow, race car are the same meaning and the same spelling when it's flipped down. The number palindromes work the same as word palindromes. So there's something like 55, 232, 101. The first question that I'll be talking about is the 2019 AMC 8 problem 13. And this question is relatively easy to solve because it's a AMC 8 problem, but it'll be good for you to warm up your brain and to have a better idea on how numeric palindrome questions are in AMC problems. So the question reads, a palindrome is a number that has the same value when read left to right from right to left. Let n be the least three-digit integer, which is not a palindrome, but which is the sum of three distinct two-digit palindromes. What is the sum of the digits of n? So I'll just be highlighting the key terms that you'll have to look for. The first one is the least three-digit integer, which is not a palindrome, so that will be n. And the next one is the sum of three distinct two-digit palindromes. So I'll just give you a few seconds to work out on how you'll be solving the question. But for those who are actually watching the video, you can just stop the video and take time to actually solve the whole problem. Okay, now I'll just be going and explaining the solution to the question. So n can be represented as a plus b plus c, and a, b, c will all be two-digit palindromes. And the positive two-digit palindromes are all multiples of 11 because numbers like 11, 22 until 99 are all multiples of 11. So we can say that n is also a multiple of 11. And the smallest three-digit number of 11 that is not a palindrome will be 110. And we will first have to check if this possible answers of this is sum of three distinct two-digit palindromes, which is listed in the question. And when we do different cases, we can see that 11 plus 22 plus 77, which are all two-digit palindromes, sum up to 110. So we can now say that n is 110, and by adding up all of the digits of n, we can get the answer of a 2. The next question is from the 2014 AMC 12A problem 15. And this problem is more harder than the previous problem that we solved. So we can have a bit more challenge on solving different palindrome problems. So the problem reads, a 5-digit palindrome is a positive integer with respective digits a, b, c, b, a, where a is non-zero. Let s be the sum of all 5-digit palindromes. What is the sum of the digits of s? So I will also be giving you a few seconds, but you can also just stop the video. Okay, now I'll be going over the answer. So we have to first notice that 10,001 and the sum of 99,999 equals to 110,000. And after noticing that, we can say that the sum of the nth palindrome and the nth to the last palindrome always equals to 110,000. So we can now solve the number of pairs of palindrome that exists in the ABCDA format. So because we have 9 different possibilities of A and 10 different possibilities of B and C, because B and C includes 0, we can say that there are a total of 900 different pairs of palindromes. And we can then try and solve the different number of 110,000 pairs there are. And because 110,000 always comes up when it sums up the nth palindrome, and the n to the last palindrome, we can say that the number of 110 sum pairs is the division of 2 of 900, which is 450. And then we can multiply 450 with 110,000 to get the sum of all 5-digit palindromes, which is S. So then after summing up the digits of S, we can get 18, which is the answer for this question. The next question is also from AMC 12. It's from the 2013 problem 22. And the problem reads, a palindrome is a non-negative integer number that reads the same forwards and backwards when written in base 10 with no leading zeros. And a 6-digit palindrome n is chosen uniformly at random, whereas the probability that n divided by 11 is also a palindrome. So for this one, we have to first think about a 6-digit palindrome n and a probability for n over 11 that is also a palindrome number. So you can just stop the video to solve the question, but I'll just be going over the solution. So if we say that n is ABCBA and the multiple of ABCBA by 11, because we have to solve 11 over n, we will be doing it backwards by actually just multiplying 11 to the number ABCBA. So when we do so, we can get this sum, and from that we can say that A plus B is smaller than 10 and B plus C is also smaller than 10. So from this, we can say that there's 9 minus B possible values for A and 10 minus B possible values for C. And then we can calculate the total amount of possibilities for the 6-digit palindrome n to form, which is 9 multiplied by 10, and we do that until 1 multiplied by 2, which allows us to get the number 330. And because the total number of palindromes in this ABCBA format is 900, as we did in the previous question, we can now divide the 330 to 900, which allows us to get the answer 30 over 11, which is number E. The next question and the last questions to this palindrome theory is the 2021 AV2 problem 1, and it reads, find the arithmetic mean of all of the 3-digit palindromes. So I'll also be just going over the solution for this one. So when we say that the 3-digit palindrome is ABA, then we can say that the possibilities of A is 1 until 9 and B is 0 until 9 and A is the same 1 to 9. And because we have to average out the different numbers in this format, then the average of A will be 5 and B it will be 4.5 and A it will be 5. And to get the arithmetic mean, we will have to multiply the different numbers to its according 100 or 10 or 1 numbers. So for 5, we will have to multiply 100. For 4.5, we'll have to multiply 10. For 5, we'll have to multiply 1. So that gets us the answer of 550. Yeah, and that is the end of our palindrome problems. And the second interesting number theory is the Fermat's-Little theorem. So this reads, if A is an integer, P is a prime number, and A is not divisible by P, then A to the power of P minus 1 is equivalent to 1 mod P. So for example, if we say that P is 5, then because 2 is not divisible by 5, 2 to the power of 5 minus 1, which equals 2 to the power of 4, is equivalent to 1 mod 5. So the question that I have is from AMC 10, problem 14. So it reads, an integer n is selected at random in the range of 1 to 2020. What is the probability that the remainder when n to the power of 16 is divided by 5 is 1? So I'll just go over the solution. So we first have to notice that n to the power of 16 is n to the power of 4 multiplied by 4. And then we have to use the Fermat's-Little theorem to figure out that n to the power of 5 minus 1 is equivalent to 1 mod 5. Then we can say that n to the power of 16 is equivalent to n to the power of 4 multiplied by 4, which is also equivalent to 1 to the power of 4, which is 1 mod 5. And because 2020 is divisible by 5, we can say that there's a total of 5 over 1 of possible n that is divisible by 5. And n to the power of 16 is equivalent to 1 mod 5, which we got over here. We can just get the answer right away by just doing 1 minus 5 over 1, which leads us to the answer of D. The last theorem that we will be going over is the chicken nugget theorem, and this has a little anecdote that allows us to see how this theorem just rised. And there was a person who went to McDonald's and they said that there's a box of 6 or a box of 11 different chicken nuggets, and the person was really hungry, so he just said, I would like to order 49 chicken nuggets, please. But the cashier just said, I'm sorry, I don't think that's possible. So we can, from this anecdote, we can say that 49 is the largest number of chicken nuggets that cannot be ordered with the combination of 6 and 11 nuggets. So this special case can lead for us to create a number theorem that a maximum value that cannot be expressed as the sum of non-negative multiples of a and b is ab minus b minus a if a and b are relatively prime. So we can also say that a minus 1 multiplied by b minus 1 divided by 2 positive integers that cannot be expressed in the form of ma plus nb, where m and n are positive integers. So from this anecdote, we can further connect that 6 multiplied by 11 minus 6 minus 11, which is 49, is the largest number that cannot be purchased. So to now go over some example problems that uses the chicken nugget theorem is the 2015 AMC 10 problem 15. So it reads, the town of Hamlet have 3 people for each house, 4 sheep for each cow, and 3 ducks for each person. And which of the following could not possibly be the total number of people, horses, sheep, cows, and ducks in Hamlet? So I'll be going over the solution. So for the town of Hamlet, we can say that there are 3 people, and for each person, there's 3 different ducks. So we can say that the total number of ducks, people, in Hamlet is 13. And for the cows, there are 4 different sheep for each cow. So then we can say that 1 cow and 4 sheep is 5. So then we can write equation 13a plus 5b, and then we can use the chicken nugget formula to find that 13 multiplied by 5 minus 13 minus 5 equals 47, and that will be the biggest number of people, horses, sheep, cows, and ducks that cannot arise. So that gives the answer of B, which is 47. The next question is from the 2019 problem, Amy problem 14, and it reads, find the sum of all positive integers n such that given an unlimited supply of stamps of denominations 5n and n plus 1 cents, 91 cents is the greatest postage that cannot be formed. This is rather a difficult problem that uses the chicken nugget formula, but I'll just go over the answers. So we can first right away use the chicken nugget theorem to find the least possible value of n that 91 cents cannot be formed. And when using the chicken nugget formula, we can say that 5n minus 5n minus 5 equals to 95. Then we can say that the smallest number of n that 91 cents cannot be formed is 24, which means that n should always be larger or equal to 24. And even though we should be unable to form 91 from these combinations of cents, but we must also be able to form the values of 92 until 96. And when we say that there's n, n plus 1 pairs to form 96, the potential sets are 24, 25, 31, 32, 32, 33, 47, 48, 48, 49, 95, 96, and 96 and 97. And these sets can form when we do simple cases. And when we think about the different sets there are, last two obviously doesn't work because they're too large to form the values of 92 until 94. So only 24, 25, 47, 48 can form the necessary values, which allows us to get the answer of 24 plus 47, which is 71. And that will be the answer to this question. That's the end of my presentation, and I hope you got a better picture on the different number theories there are in different AMC or AMU questions. Thank you for listening.